So bulk modulus, which is basically bulk stress divided by bulk strain, is expressed as minus delta P divided by delta V by V. Now it is given that the bulk modulus of steel is around 160 gigapascals. Can one of you tell me how much the factor giga is?
1000.
How much?
1000, sir.
1000 is kilo. Okay, 10 power 3 is kilo, 10 power 6 is mega, 10 power 9 is giga. So bulk modulus of steel is 160 into 10 to the power of 9 pascals or Newton per meter square. Fine. So that is minus delta P divided by delta V by V. So suppose you increase pressure on steel, on an object made of steel, okay, then the relative change in its volume, delta V by V, would be negative of delta P divided by 116 to 10 power 9. So if you want to bring about, or if you want to create any significant change in volume in an object made of steel, okay, uh, I'm not talking about empty objects made of steel. Suppose there is uh, a hollow sphere made of steel, made of a thin layer of steel, you can easily compress it. Okay, you can easily deform it. That is not what we are talking about. If you compress a hollow sphere, no, for example, suppose there's a hollow sphere like this. If you compress it, like you make a dent in it by hitting it with a hammer or something, you may make it somewhat like this. Okay, this is quite easy actually. Okay, by hitting it with a hammer, you can do it. Okay, or sometimes like if it is made of a very thin layer of steel, you can just smash it against the wall or the floor and make a dent in it. That's quite easy. You might have observed also steel utensils, they get dents very easily when they fall on the floor. Now here, obviously the volume of the sphere has decreased, the volume inside has decreased. This is not the change in volume that we are talking about. We are talking about change in volume of the material steel. Okay, that if you want to compress, okay, or you consider a ball made completely of steel, that one if you want to compress, then okay. So if you want to bring about a significant change in volume of steel, understand how much pressure you need to create. Okay, if you want this to be significant, the relative change, denominator is 160 into 10 power 9. In proper scientific notation, you would write it as minus delta P divided by 1.6 into 10 power 11. So you will need to create a pressure change of the order of 10 power 11 pascals, which is huge. So if you want to actually compress steel, that is the kind of pressure that you need to apply. Okay. Well, not every material has such a high bulk modulus. Okay. So not every material requires that much pressure to be compressed. Fine. For example, rubber. Rubber is very easy to compress. Let me check the bulk modulus of rubber. 9.8 into 10 power 8 Newton per square meter. 9. Okay, that is significantly low compared to that of steel. So bulk modulus of rubber. They gave 9.8. Let us take it as 10 into 10 power 8. That is close to 10 power 9 or less than 10 power 9 Newton per meter square. But for steel, it was 160 into 10 power 9, 160 times greater than rubber or stronger than rubber. Okay, fine. So let's solve some problems based on this. So basically what happens if you increase the pressure on an object, its volume decreases. If you decrease the pressure, its volume increases, it will expand. Okay. So first question. Calculate the pressure. Okay. Pressure means change in pressure that must be applied on a rubber sphere to decrease its volume by 2%. Okay, you use this bulk modulus of rubber, 10 power 9 Newton per meter square. Okay, try this all of you. I'll give you 2 minutes. Solve very carefully. Use the formula for bulk modulus. I'll write it here. Minus delta P divided by delta V by V. So understand what is asked in the question, what is given in the question, and try to relate them through this formula. Do it. See, the bulk modulus is known to us. You are asked delta P. Okay, this is known. If you know this, then you can answer delta P. It is told to you that the volume of the rubber sphere must decrease by 2%. Okay, how do you put that in mathematical form? Vanilla, can you tell me how to write percentage change in volume mathematically?
So del V by V into 100.
Correct. Percentage change in any quantity, let's say X, it is expressed as relative change delta X by X multiplied with 100. That becomes percentage change. Now we want its volume to decrease by 2%. That means the percentage change in volume should be minus 2. That is how you take it. Okay. So indirectly delta V by V is given to you. So delta V by V becomes minus 2 by 100. That's all. Substitute it there. You will get the change in pressure that is needed. Okay. Solving, I think you can do. Next question. Suppose the bulk modulus of some material is given to you as, let's say 10 power, okay, 10 power 7 Newton per meter square. Calculate the pressure that must be applied on a sphere made of this material to decrease its radius by 3%. Okay. Or, okay, let's take 1%. So this time, instead of volume, you are asked the question in terms of percentage change in radius. Okay. So think of how to relate them, how volume change can be related to radius change, and then you can relate it to bulk modulus and find out the change in pressure. Okay. Solve this carefully. I'll give you all 3 minutes. So you are given the bulk modulus and you are asked the change in pressure, which would result in a certain change in radius, certain percentage change in the radius. Now bulk modulus relates the change in pressure to the relative change in volume. Okay, so you can relate it to percentage change in volume also. But the question is given in terms of percentage change in the radius. And you know radius is related to volume or volume is related to radius. How? We are talking about a sphere here. Volume of a sphere is 4 by 3 pi r cube. Okay. Now 1% is a small change. Fine. That's why I asked you to revise ideas from errors. But anyway, even if you don't remember those, remember this. If you want to relate percentage changes, not just percentage changes, if you want to relate small changes between two quantities, okay, remember this forever. If you want to relate small changes between two quantities, first write the equation relating those quantities, differentiate it, simple. Okay, because if you differentiate, for example, let's say you have y as a function of x. If you differentiate it, you will get dy and dx terms. Dy is a small change in y, dx is a small change in x. That way you can relate the small changes between them. So it's no big deal. Even if you forget, just remember this, that differentiation can help you relate small changes in one quantity to small changes in another quantity. Now let's do that for volume and radius. We know V is 4 by 3 pi r cube. We want to relate change in volume to change in radius. So you differentiate this equation. With respect to what you differentiate is your choice. There are two terms here, volume and radius. You can differentiate with respect to volume, you can differentiate with respect to radius on both sides, or you differentiate with respect to some other variable also, it won't matter. Okay. Let's differentiate with respect to some other random variable, let's say x. Left hand side, you have only v. If you differentiate it with respect to x, it becomes dv by dx. Okay. Right hand side, you have 4 by 3 pi r cube. Differentiate it, 4 by 3 pi is constant. R cube, if you differentiate with respect to r, it is 3r square. But if you differentiate with respect to x, it becomes 3r square into, sorry, yeah, dx by, dr by dx. Huh. Chain rule. Now, what do we actually have to relate to solve this problem? We have to relate relative change in volume delta V by V to relative change in radius. In question, they have given percentage change. You can convert it to relative change. So indirectly, delta R by R is given to you. But you need to convert that to delta V by V to find out the change in pressure. Okay. Now, I told you, you can differentiate with respect to any variable. We differentiated with respect to X. It will get cancelled. Dx will get cancelled on both sides. Okay, now readjust this equation. 3's get cancelled. You get dV is equal to 4 pi r square dr. Okay, but what did you actually want? You wanted relation between delta r by r and delta v by v. Fine. So what you can do now is, after differentiating, divide the equation by the same thing on both sides. You can divide it by volume, or you can divide it by radius. It's your choice. Dividing by volume will make things easier for us. If you divide by volume, left hand side directly becomes dv by v, which is similar to delta v by v, small change. Right side also you have to divide by the same thing. You can't divide by two different terms on both sides, then the equation will become invalid. Right side also you have to divide by volume only, but write it as 4 by 3 pi r cube. How does this help? 4 pi's cancel, 3 goes to the numerator. The right hand side becomes 3, okay, r square and r cube, 1 r will remain, dr by r. So you get dv by v is 3 times dr by r. So what did you do effectively? You relate the relative change in volume to the relative change in radius. Simple. And this is what we learned in error analysis also, error propagation. When you have x is equal to a to the power of m, then the percentage change in x becomes m times percentage change in a. That is what we had learned there for small changes. And the same is what now also we are getting the same thing. Volume is 4 by 3 pi r cube. No, for percentage changes, these constants won't matter. So effectively, what did you get finally? Percentage change in volume is 3 times the percentage change in radius. Okay. We got relative change into 100 on both sides will give us percentage change. That's all. So see, you have to keep at least these ideas in mind. If you want to relate small changes, you can use differentiation. Keep that idea in mind and work a little bit, you will be able to solve the problem. You will have to put that much effort at least. Not everything is just recollect and uh, answer. Okay, you have to put a little bit of effort, do a small derivation, then you can. Okay, so relative change in volume is 3 times relative change in radius. Now the question is saying radius should change by 1%. So delta r by r into 100 is 1. So you can say delta r by r is 1 by 100. Then that means delta v by v will be 3 by 100 because relative change in volume is 3 times the relative change in radius. That's all. Once you have this, substitute it in the bulk modulus formula. The bulk modulus is given to you in the problem. You can tell how much is the change in pressure needed. Vanilla, is this what you did?
Yes, sir.
Okay, good. Next, let's try another problem, similar one. Let's say the bulk modulus of a material is 10 power 6 Newton per meter square. Okay, let's assume a sphere itself. On which the pressure increases by, okay, we need a significant change in pressure to create a significant change in volume. So let's say the pressure increases by 10 power 5 Newton per meter square. Take the bulk modulus as 10 power 7, not 10 power 6. And pressure increased by this much. Now, if you increase the pressure on a sphere, it will shrink. It will get compressed. Volume will decrease. One of you tell me, what happens to its density? Increases or decreases?
Increases.
If you compress something, its density increases because the same mass will now be occupying a lesser volume. It will become denser. I want you to find out the percentage change in its density. Okay, try this. Right. You are given the bulk modulus of a material and the change in pressure on a sphere. So delta P is given and beta is given, and you are asked to calculate the percentage change in density. You know, bulk modulus relates change in pressure to relative change in volume. And from that, you can get the percentage change in volume also. But you are asked to calculate percentage change in density. So you need to first think of the relation between volume and density. Okay. Now, when an object is compressed or stretched, it's a solid object, its mass is not going to change. So using that, you can relate density changes to volume changes. You know, density, let's use the symbol rho for density. Density is mass by volume. So you can say density is mass multiplied with volume to the power of -1. That's all. Therefore, the percentage change in density will be -1 times the percentage change in volume. Okay. Now, in case you don't know how this is derived, you can do it this way. As I said, to relate small changes, you can use differentiation. Now, rho is m times v power -1, or let's use rho is m by v itself. Differentiate both sides. Okay. So left hand side, d rho by dx, differentiating with respect to some unknown variable x, you get m times derivative of 1 by v is -1 by v square dv by dx. Now you can cancel dx. That's why it doesn't matter with respect to what you differentiate. And you can write this as d rho is minus m dv by v square. Fine. Now d rho is the actual small change in density. We don't want that. We want percentage change or relative change. Now, how to get relative change? You divide by density itself. And if you're dividing by density on one side, you should divide by density on the other side as well. So left hand side becomes d rho by rho is equal to minus m times dv by rho v square. Okay. We want to relate relative change in density d rho by rho to relative change in volume dv by v. So we don't want rho on the right hand side. Okay. Now we know density is mass by volume. We'll substitute that. So in place of density, you substitute mass divided by volume. Mass gets cancelled, 1v gets cancelled. You'll get minus dv by v. That's all. And then multiply with 100 on both sides. Percentage change in density becomes negative of percentage change in volume. That is what I had written here. Okay. Now, you are asked to calculate the percentage change in density. So we'll first calculate percentage change in volume, put a minus sign before it, you get the percentage change in density. Bulk modulus is given as 10 power 7 is equal to minus the change in pressure. The pressure is increased by 10 power 5 minus delta P divided by delta V by V. So that makes delta V by V equal to negative of 10 power -2. So percentage change in volume becomes -1%. It makes sense. You are increasing the pressure on the object, so that will decrease its volume. That's why the percentage change in volume is negative. And we just derived that percentage change in density is negative of percentage change in volume. So that becomes 1%. That means the density increases by 1%. Okay, makes sense. If volume decreases for the same mass, that means it becomes denser. Density increases. And the percentage change is 1%. Next, let's solve one percentage change based question based on Young's modulus and length of a wire. Right. Consider this. The Young's modulus of steel, okay, based on experimental data, is 1.9 into 10 power 11 Newton per meter square. And you know Young's modulus by definition is the ratio of longitudinal stress to longitudinal strain. The formula becomes perpendicular force per unit area of cross section divided by change in length by the natural length. Okay. So calculate this. You are given a steel wire of cross sectional area 4 millimeter square. Calculate the force with which the wire must be stretched to elongate it by 2%. So this 2% is the percentage change in length of the wire. Okay. Try this all of you. I'll give you 2 minutes. Right. You are asked the force with which the wire must be stretched to elongate it by 2%. Okay. So the percentage change in length is given to you. Percentage change in length is relative change in length multiplied with 100, that is given as 2. That means the relative change in length should be 2 by 100. Okay. All other terms required are given to you. Young's modulus is given. Area of cross section is given. Directly substitute. So y is equal to F perpendicular by A divided by delta L by L. So F perpendicular by A becomes y delta L by L, or you can say F perpendicular becomes y delta L by L multiplied with A. That's all. Young's modulus is given 1.9 into 10 to the power of 11. Yes, that is in SI units. Relative change in length we want is 2 by 100 multiplied with area of cross section 4 millimeter square. Now everything is written in SI units. Millimeter square, millimeter is 10 power minus 3 meter. When you square it, it becomes 10 power minus 6 meter square. So into 10 power, okay, 4 into 10 power minus 6. 6. Right. So 10 power minus 6, 10 power 11 is 10 power 5. Divided by 100 is 10 power 3. 2 into 4 is 8. 8 into 1.9. 8 to 15.2. So 15.2 into 10 power 3 newtons. Vanilla good. Okay. So you can write it as 15.2 kilonewtons also. If you stretch this particular steel wire with that much force, its length would increase by 2%. See, in this chapter solids, these are the kind of calculations that you are expected to do. Okay, I'll send you a worksheet with problems like this. You open any book also, like your textbook or maybe HC Verma or that JEE main book that I asked you to refer. Any one of them, you'll find problems like this. Okay, or some theory questions can be asked. Okay. Just one more concept. As of now, this concept is not there in NCERT, but for entrance exams, it's quite common. Poisson ratio or Poisson's ratio. This is applicable only to cylinders. As far as your syllabus is concerned, okay, syllabus for mains or NEET is concerned, this is applicable only to cylinders. Just a moment, let me take the diagram of a cylinder. Okay. Assume there is a cylinder whose natural length is L0, means when there's no stress applied on it, its length is L0, and the diameter is D0. Fine. When you apply a longitudinal stress on this cylinder, you will be elongating it. Okay. But in that process of elongation, naturally, some decrease in diameter would happen. It would become thinner. You can observe this clearly in case of a rubber band. Right? So when you stretch a cylindrical wire, its diameter will decrease. If length increases, diameter decreases. If you do it the other way, if you compress it, the length decreases, it will bulge out, diameter will increase. Okay. Of course, it won't increase uniformly throughout, but for now, let us assume it is uniform. So if length changes by delta L, okay, and it is positive, then the diameter changes by delta D, and that would be negative. If length increases, diameter decreases. And reverse, if length decreases, diameter increases. These two will be of opposite signs. Okay. The Poisson's ratio of a material, okay, it's given for a material actually, denoted by the symbol sigma. It relates, okay, sigma relates relative change in length to the relative change in the diameter. Simple. Okay. And how does it relate? It is the ratio of relative change in diameter to the relative change in length. And you know, if when one is positive, the other will be negative. So just to keep this sigma value positive, we include a minus sign. So minus delta D by D naught divided by delta L by L naught. So relative change in diameter divided by the relative change in length. That's all. You can multiply by 100 on in both the numerator and the denominator. Then it becomes percentage change in diameter divided by percentage change in length. Simple. But questions based on this can be asked in many different ways. So remember, Poisson ratio of a material relates the relative change in length to the relative change in diameter of a cylinder made with that material. Okay, it depends on the material only, sigma value. Fine. Let's try to solve problems based on this. As I said, it's meant only for cylinders, so they won't ask you about any other object. So first, we know that if length is increased, diameter decreases. Let's assume the length of a cylinder increases and diameter decreases such that its volume remains constant. Okay, I think this will be slightly high level. We'll do this next. Okay, let's solve this problem first. Poisson ratio of a material, let's say it is given as 0.4. And the relative change in length, let's take it as maybe 0. Okay, delta L by 0.1. Okay. When some stress is applied on the cylindrical object, the relative change in its length is 0.1. Poisson ratio is given 0.4. Now, from Poisson ratio and relative change in length, you can find out relative change in diameter. And if you know what is happening to length and diameter, you can tell what happens to volume. So I want you to find out, calculate first relative change in the diameter. And then based on that, relative change in volume. And based on that, by multiplying with 100, you can tell the percentage change in volume also. Okay. Do this, all of you. I'll give you 2 minutes. Answers so far, let's see. At least relative change in diameter, anyone? That I think you can directly relate, no, from directly calculate, no, from the formula for sigma. Okay, maybe you all didn't note down the formula. Note this down, all of you. Poisson ratio sigma is minus delta D by D naught divided by delta L by L naught. Okay. So from this itself, we can say that delta D by D naught, the relative change in diameter will be minus sigma delta L by L naught. Directly substitute. So negative of sigma is 0.4 and delta L by L naught is 0.1. So negative 0.04 is the relative change in its diameter. And why is it negative? Because length has been increased, diameter will decrease. And because it is decreasing, the relative change is negative. Okay. Next is the relative change in volume. What is the shape that we are considering? Cylinder. One of you tell me, how do we express the volume of a cylinder? You can tell in terms of radius and length, area of cross section and length, diameter and length, any one of them.
Sir, volume
Pi
of
r square
cylinder.
into x.
Rishi, what were you asking?
Cylinder, right? It's pi r square, right?
Pi r square L, correct. Okay. So pi r square L. You can also write it as, see, radius is half of diameter. So this becomes pi d square by 4 into L. That's all. Now you need relative change in volume. What do you know? The relative change in length is given to you already. And the relative change in diameter you found out. Okay. That is why I wrote the formula this way in terms of diameter. Now we know relative changes in diameter and length. We need relative change in volume. Okay, simple. If you are comfortable with error analysis, you will be very comfortable with this. Those of you who know who remember what we did in error analysis, you can directly write like this: percentage change in volume or relative change in volume. Delta V by V simply becomes 2 times delta D by D plus delta L by L. Suppose you didn't know this, you will have to use calculus. As I said, you can use calculus, you can use differentiation to relate small changes between quantities. Now volume depends on diameter as well as length. You can't write it only in terms of length or only in terms of diameter. Okay. So differentiate this equation. Let's differentiate it with respect to some random variable x. So left hand side becomes dv by dx. Right hand side, pi by 4 is a constant. You have to differentiate d square L, both of which are variables. Length changes, diameter also changes. Okay. So you have to use the product rule. How do you use product rule? U dv by dx plus v derivative of d square. Okay, I should have used some other symbol in place of d. Let me use capital D for diameter just to avoid confusion. The differentiation d and diameter d, to avoid the confusion, I'll use capital D. So u dv by dx plus v du by dx, derivative of d square with respect to x. Okay. Pi by 4 times d square dl by dx plus L times derivative of d square becomes 2d, but that is with respect to capital D. If you differentiate with respect to capital D, we are differentiating with respect to x, so d capital D by dx also will be there. Okay. Now you can cancel dx throughout. And what you need to relate according to the question is the relative changes. You are asked to find out relative change in volume. Okay. So you divide by volume on both sides. So left hand side becomes dv divided by v is equal to right hand side pi by 4 into, what are you left with? Capital D square dl plus 2ld times d capital D. Okay. You have to divide this side also by volume. How much is the volume? Pi d square by 4 into L. Okay. Pi by 4 cancel. What will you be left with? First term, d square dl divided by d square L. D square cancel, you'll get dl by L. Plus second term, 2ld dd divided by d square dl. 1d and 1l will get cancelled. You will be left with 2 times d capital D by capital D. And this is what I said, relative change in volume. Okay, let me use delta in place of d just to avoid confusion. Relative change in volume is relative change in length plus 2 times the relative change in diameter. Okay. If you had remembered what we did in error analysis also, you would have done the same thing. But see, it is understood that you people are not comfortable with this. Okay, that is why you were not able to solve this problem. So it is also understood that you need to put some effort on this. Okay, so I'll give you a few questions tomorrow. Saturday, Sunday, you have 2 days to practice. Tomorrow's worksheet, I'll put some questions like this. You will first have to relate relative changes and percentage changes between quantities. You should be very comfortable doing that. Then you can easily solve questions from this chapter. See, gravitation, solids, these are some of the smallest chapters in your 11th syllabus, not just 11th, in your entire syllabus. So these automatically become scoring chapters. Very few concepts are involved. You just need to know how to apply those concepts and get the answer. Fine. So work on it a little bit over the next 1-2 days. Saturday, Sunday, you sit and work on this chapter completely. So in this problem, we got relative change in length that was given to you as 0.1 plus 2 times relative change in diameter. We derived it as 0.04. 0.04 into 0.08. So effectively it becomes 0.18. That is the relative change in volume of the, what do you call, cylinder. Okay, based on its Poisson ratio and the relative change in length that you created. Okay. So if sigma is given, Poisson ratio is given, and the change in length is given, you can find out change in diameter and tell what happens to change in what happens to the volume. Means you can find out the change in volume. Now the reverse. Okay, this slightly tricky question that I was talking about. The length of a cylinder is increased and its diameter automatically decreases. Okay, that need not be mentioned. The length increases and diameter decreases such that the volume remains constant. In that case, okay, calculate the Poisson ratio of the cylinder. Try this, all of you. So this time actual changes are not given to you. So assume length changes, relative change in length is some x. Volume remains constant, means change in volume. Can one of you tell me if volume remains constant, what is the relative change in volume?
0, sir.
0. That is the only thing that is given to you. You assume some relative change in length. Volume did not change. Based on that, you find out relative change in diameter. You know how to relate volume change, length change, and diameter change. We did that in the last problem. Do it and then get the ratio of relative change in diameter to relative change in length. That will give you sigma. Try this, all of you. I'll give you 2 minutes. You are asked to calculate the Poisson ratio. We know Poisson ratio is negative of relative change in diameter of the cylinder divided by the relative change in length of the cylinder. Now you are told that volume remains constant. Volume is pi by 4 d square L. So relative change in volume is 2 times relative change in diameter plus relative change in length. This is 0. That's all. Send delta d by d to the other side. So minus 2 delta d by d is equal to delta L by L. Now send the 2 this side, delta L by L that side. Minus delta d by d whole divided by delta L by L simply becomes 1 by 2. That is 0.5. And this by definition is Poisson ratio. Simple. Okay. Actually, this is an interesting answer. I mean, you need to remember this. If Poisson ratio is 0.5, that means the volume of the cylinder does not change. You can solve this problem in reverse also. Okay. You take sigma 0.5, take some change in length. You will see that the change in diameter will be in such a way that the volume does not change at all. Now, the last problem we solved, we assumed Poisson ratio to be 0.4, which is less than 0.5. And see what happened. We stretched the object, and if we stretch the object, we see that the relative change in volume is positive. So when Poisson ratio is less than 0.5 and you stretch an object, its volume increases. Overall volume increases. If Poisson ratio is exactly 0.5 and you stretch an object, its volume does not change. Okay. Its length will increase and diameter will decrease in such a way that the volume remains constant. Fine. Now you can try another problem. You can take Poisson ratio more than 0.5. Take some 0.6, 0.7 and then check. You will see that its volume actually decreases. Okay. Why? You can justify it like this. Poisson ratio is negative delta d by d divided by delta L by L. Now if this is 0.7, let's say, that means relative change in diameter is minus 0.7 times relative change in length. Let it be. Then the relative change in volume, we know by definition it is delta d by d, means from the formula of volume of a cylinder, it is 2 times delta d by d plus delta L by L. Now delta d by d is 0.7 times of delta L by L. Substitute that here. Then 2 into 0.7 becomes 1.4. And this comes with a negative sign, no? Okay, wait. No, Yeah, this comes with a negative sign. So effectively, this will become minus 0.4 times delta L by L. So if length increases, the volume actually decreases. Fine. So you can be asked some questions based on these cases also. So you can remember it this way. If Poisson ratio is less than 0.5 and you increase the length, then you will see that the volume also increases. If Poisson ratio is exactly 0.5 and you increase the length, you will see that the volume does not change. Okay, remains constant. And if Poisson ratio is greater than 0.5, when you stretch the cylinder, its volume actually decreases. Fine. That is all there is in this chapter. Longitudinal stress, longitudinal strain, they are connected by Young's modulus. And in case of longitudinal stress and strain, there are many different things that you need to know. Non-uniform stress, how to deal with it, how to find out strain in case of non-uniform stress, how a stretched wire can be compared to a spring. Okay. How to find out potential energy in that stretched wire. Where does the extra energy go when you stretch something? It gets converted to heat. They can ask you direct questions like that also. How much is the heat generated when a wire is stretched by applying certain amount of force? So based on the force applied, you first find out how much it elongates, work done by the external force, energy stored in the stretched wire. The difference is the heat released. How much work you are doing, how much energy is getting stored. The difference is the heat released. Such questions can be asked. Then we talked about stress strain curve, breaking stress. Okay, that is important. Okay, this was some other question in here. Last class, we solved some problems based on breaking stress, and then tangential stress, tangential strain related by shear modulus, bulk stress, bulk strain related by bulk modulus. Okay. We'll be using these terms again. In the next chapter itself, fluids, we'll talk about tangential stress, tangential strain, bulk modulus, all those things. Okay, we'll stop it here for today. I'll send you a worksheet tomorrow with problems from this chapter. Make sure you solve all of them. First, revise the theory, then solve all the problems. Be thorough in the chapter. It's a small chapter. Fluids will be slightly lengthy, and as I said, next week I'll be taking 4 classes. Mostly they'll be on Monday. You will have. We'll see. Either Tuesday or Thursday. One of those days I will have to take the extra class. No, Monday, Wednesday, Friday you will anyway have classes. Okay, I'll inform. We'll try to finish fluids as much as possible. In 1 week, if it is completed, good. No, 4 classes won't be enough anyway. We'll need at least 6 to 7 classes. So 2 weeks we'll try to finish it off. Okay, thank you all. We'll continue in Monday's class.